Hi, my name is Sharon Katz. In this video, we'll talk about VIPT caching and its advantages over physical memory caching and virtual memory caching. Let's start with the most simple case of caching, which is physical address space caching. With this method, we go from the CPU and ask for a virtual address. We go through the TLB, which holds caching of addresses, and we convert the virtual address into physical address. Now we have a physical address and we check if we have it in the cache. If we have, then we are happy and we have a hit. If not, we go to the DRAM. In this case, we pay a lot because accessing DRAM is significantly more expensive than accessing the TLB or the cache, which are closer memory, and so hitting the DRAM is expensive and getting a hit is what we want. So what are the disadvantages here? We need to go through the TLB in order to get a cache. So we actually do two steps here. One is the translation from virtual address to physical address through the TLB, and the other is going to the cache. This may be considered as two CPU cycles or double action that we don't want. So let's try something else. Let's cache the virtual address. It looks much simpler. We go from the CPU, we take a virtual address, and we try to look for the cache, look for it in the cache and see if we have a hit. If we have a hit, we're happy. If not, we go to the TLB and then to the RAM. Now in this method, going to the TLB is not expensive because it is relatively very small relative to the accessing the DRAM. I mean, if we actually going to get it from the DRAM and pay this expensive method of getting the memory, we don't mind doing it via the TLB. So it looks very good. However, there is a problem here. Remember, we have more than one process. We have many processes running at the same time. Each of them has its own virtual address space. So we have a problem with coherency here. It is complicated to share between processes. We will need to invalidate the cache every time we switch processes, which may come as something that will be inefficient and we will gain nothing here. So this is where VIPT comes. It tries to solve everything by merging the systems. So we go from the CPU, we take a virtual address that we have per CPU, and we do two things at the same time in parallel. We take the offset part of the address, and the offset will give us we'll take the offset part of the address and we'll go to cache, and we will get two things. One is the data, and another one is a physical tag that is held in the cache as well as the data, which we will use to compare to what we get from the TLB. Now, at the same time, we go to the we take the higher parts of the address of the virtual memory address, which is actually the virtual page number, and we go to the TLB. Now, the TLB will give us a physical memory, which should be identical to the physical tag that we get from the data. So in the cache, we actually hold the data itself plus the physical memory address that we compare with the TLB. Think about it. Here we have done, we did one operation, we did two operations, but in parallel. So this could be done in one CPU cycle. So we know if we have a hit or a miss in one CPU cycle. If we do have a hit, we'll know it immediately, and we are happy. If not, then we go to the DRAM and do the same thing. So this summarizes what VIPT does and why we should use it, and why modern CPUs use it over physical caching or virtual caching. Thank you very much.